So welcome back. Yesterday I finished with your last homework. It is now available. Bum, bum. It is worth, I want to say 16 or 17 points. It's the highest one, since we're sort of building to like the finale of stuff to know how to do.
Is it a beast?
I don't think so. I could be wrong, but I don't think so. What I do know is that you have 2 weeks and a day to finish it. So if it is a beast, I fully expect you to ask for help rather than banging your head against the wall or throwing anything. Deal? Deal. Okay. It is going to be a general linear model with interactions, 2 interactions among quantitative predictors. So this that we've been talking about. So I thought it might be good to review this as a concept in lieu of that, and then we can move on to interactions with categorical predictors that take more than one contrast. So moderation, let's start there, big picture. What does moderation mean? Anything that comes to mind? If I say the word moderation, what jumps into your mind? Interaction terms. So interaction terms is how we operationalize the idea of moderation. What is an interaction term? Those are kinds.
Oh, okay.
Like how would I make one in a model?
Multiple things.
Yeah, 2 variables multiplied together. So in old school software, they literally made you do that in your data set. If you want to do it the fast and easy way without making a new variable, in SAS, what do you need to put? What symbol that joins the 2 variables to be interacted in SAS? Remember? It's okay if you don't remember. It's a special character. It's above the 8 on an English keyboard. Asterisk. In Stata, what is it? Anyone? Pound or? Hashtag for the younger ones here. Hashtag what?
Moderation.
Yes, I like it. Hashtag moderation. Exactly. So moderation means interaction term. An interaction term is the multiplicative combination of 2 or more variables. So in terms of terminology, if it's 2 variables interacting, we call that a 2-way interaction. That's all the level of complexity that we've talked about here. You can also have 3-way interactions, which is 3 variables multiplied together. In order to do that, you'd have to have all possible 2 ways and all possible main effects. Conceptually, what kinds of hypotheses lend themselves to moderation? We talked about one example last time with forgiveness and stress and disease severity. Remember that? Can you come up with some words that lend themselves to the idea of moderation?
Controlling for, is that pregnant?
Not exactly. Controlling for is the idea that multiple predictors are in the same model and you're looking at their unique effects. So that would be true regardless of whether you have an interaction term. So interaction is like above and beyond just controlling for. It's another layer of complexity. So in the example that I gave you, we were looking at forgiveness and stress and disease severity. Is stress bad for you? Like in that example? Could you just say yes or no unilaterally? Or do you need to give a caveat? You say caveat? Yeah, it depends, right? The idea of moderation is it depends if you say if a predictor matters. The value of the interacting predictor dictates the effect of the other predictor. So if I have, let me pull up my virtual chalkboard, as it were. So if I have something like, I'm going to do my equations. Do you remember how to do equations? Remember this? We did this a little while back. Alt equal gives you your equation editor. Y. So if I'm going to do my equation properly, like in a book or in a results section or something like that, I need subscripts, right? So underscore is how do you make a subscript. So if I go y sub I equals What comes first in a general linear model equation most of the time? Intercept, which we usually use what for? Yeah, so I do slash, the one that's above the enter, beta, and I hit the space bar, and it jumps into the character, underscore 0, plus, if I have a slope for, we'll go beta 1 x sub I, plus, we'll do another beta, we'll go 2 times, let's go z for another letter, plus, do another beta, 3 plus x sub I, nope, back up, x sub I times z sub I. And what else do I need to make this a general linear model equation? What goes at the end? E. What does E indicate? Residual or error. It's the idea that this part, the model for the means, the fixed effects, only gets you so far. E represents the idea of a leftover difference between what is predicted and what you actually have in Y. Okay, did I forget any subscripts? Do any of my betas need subscripts? Hang on, didn't mean to put a plus sign here. Nope, not that one. There, that looks better. I'll just put these next to each other because it looks a little weird to have them separated. There we go. Did I forget any subscripts? Do my betas need subscripts? Yes or no? Not in this class. No betas? These are my fixed effects, right? I've got 4 in total. Beta 0 fixed intercept. I've got 3 kinds of slopes. So beta 1 and beta 2 are special cases of slopes that are conditional, simple, meaning that they are not only after controlling for all the other predictors in the model, but they're also, this is the, beta 1 is the slope for x, specifically when what is true?
Z is 0.
Z is 0. Likewise, beta 2 is the slope of z when x is 0. Yes. So these betas do not get I subscripts because they apply to everybody equally. Everybody's predicted value uses the same beta coefficients to make it happen. What differs per person are the random variables that they contribute. Their score on Y, their score on X, their score on Z, and E is a consequence of those things. Okay, with me so far? So, what does beta 3 do? Now this is where, Cole, you started in. The kinds of beta 3s, the kinds of interaction terms, there's 4. More positive, less positive, more negative, less negative. And what is beta 3 applying to that it makes it more positive, less positive, more negative, less negative? Which slopes? Beta 1 and beta 2. So beta 3, the interaction slope, makes beta 1 more or less positive or negative as a function of z. Beta 3, the interaction slope, makes beta 2 more or less positive or negative as a function of x. So the idea that whether or not x matters depends on what your z value is. That's what this model is saying. Whether or not, or the extent to which z matters, depends on your value of x. That's also what this model is saying. Either one of those interpretations is equally correct. You could explain it both ways, or you could pick one way and go with that. Usually one way aligns itself to your research question a little better. But either one is technically correct. So yes, moderation implies the addition of an interaction term like this, which is a multiplicative combination of variables that gets its own fixed slope in the model. And as we talked about last time, beta 3, is this conditional or unconditional? This one, this beta 3 is unconditional because there's nothing else in the model that contains x and z. So beta 3 affects the beta 1 slope the same way for everybody. Beta 3 affects the beta 2 slope the same way for everybody. Okay, how are we doing? Yeah? So the model tells you specifically what beta 0 is going to be your expected outcome when all the predictors are 0, right? So this is the y hat predicted outcome when x is 0 and when z is 0. But the model tells you what it would be for any other value, right? You can write a special statement to ask it, what would y hat be if x was 5 and if z was 3, right? You could figure that out for any combination. What are the 3 ways that you can think of to figure out what a predicted y would be for any level of a predictor? I taught you 3 different ways. And you're going to get a chance to practice this on your last homework. And you know what? I prefer two of the ways over the third, but because I'm going to ask for standard errors. So what is the way that if I were mean and made you do hand calculations? You could get out a calculator and do this, right? Or you could build yourself a spreadsheet, right? I did that for you, I think, in the beginning of example 7. You can create predicted outcomes just from the constants and the values of the predictors, but coming up with a predicted standard error is a little trickier. There is a formula for it, but again, you have to know the formula and implement it correctly. So what are the other ways that you can get predicted outcomes and the standard errors that go with them?
Fake people.
Fake people. Tell me about fake people. And you can throw the question to anyone else too. We'll be like phone a friend.
I knew the word.
And if you want, you can literally throw the question. You can do like a pass the potato thing here.
That's dangerous.
What? These are my laptops. What do I care?
You add them in, but you don't use them in the calculations.
Close. You add them into the data set. You give them an ID variable, and you give them predictor values, but you don't give them outcomes. Then when you run the same model, all software packages allow you to add an option to create a column of predicted values in a data set. They do not mess up your model because they don't have outcomes. They can't be used to find out what the slope should be, but they do get the predicted outcomes. And so then they're sitting nicely in the data set. So that's what I would recommend if you're using SAS. If you're using Stata, you can do so more directly with one line of code. It starts with an M. Margins, yeah. In Stata, you can say, give me the margins for this range of X values, this range of Z values, and it will spit them all out. In SAS, if you wanted to do the same thing, it's an estimate statement. So in example 7, for instance, the first model that just has main effects, these statements would be how you get predicted values for different combinations of variables. So every predictor variable, main effect or interaction, the whole model goes into these statements. Anything that you leave out is implicitly held at 0. So the downside in SAS is that you have to write one statement for every single value you want to estimate. That one statement gives you both an estimate and a standard error, whereas in Stata, you can ask for this for a range of values with one line of code. That's why I slightly prefer fake people, but that requires a little bit more coding. Fake people requires you to, let me find it here, create fake cases. Here we are. Add them, save them to a data set, merge the data set, and then run the model on the combined data set and add a line of code that asks for predicted outcomes. So on your very last homework, I don't care which way you do it, but you have to do it through code because I'm asking for standard errors. Calculating stuff by hand is a bad idea. The computer's better at it. Let it do it. Okay, so this is our type of moderation model. This is the type of model that you'll get some practice with on your last homework, including predicted values. All right. Questions so far? No?
So comparatively is fast with 50 or faster?
I think it is. So the problem with, so this is just a question of efficiency, right? There's not a right or wrong way necessarily. Like when you write out a statement like this, let's say that I decide to take out one of my predictors or I decide to add an interaction term or something. I have to change every single statement. And if I want to have a plot that has more points on it, I have to add additional lines. It's tedious in that sense. Whereas if I do fake people, if I have a sense of what kind of picture I want to make, I write people that would show up in the picture. And then if I change the model, the predictions automatically get updated. So all I have to do is change what the model holds, and this new data set of predicted outcomes adjusts to meet it. So there's fewer things that you would have to change. That's all. And when you have interaction terms in your model, this is the kind of thing that you have to be able to do, is to make pictures. People will depend on your pictures. Okay. Other questions? Okay, so let's look at example 7. We almost finished it before break, but not quite. Kiwi got in the way, as I recall. We were going to finish it on Thursday, but better late than never. So let's start on page 5. Example 7, page 5, about halfway down is where I am. So this is the same data set we've been playing with for a few weeks. 550 fake older adults who vary in age, grip strength, gender, and a 3-category version of dementia: none, future, or current. This particular model that we're working with has main effects of all the predictors plus an interaction term between age centered at 85 and grip strength centered at 9 pounds per square inch. So we went through quite a bit of this before, but would it be good to go over it again? I'm assuming you don't have like photographic memories that it logged just perfectly the first time? Yeah, me neither. Especially after a few weeks. So we have, this is our line in SAS. It looks virtually the same in Stata except for swapping a hashtag for this asterisk. I have some additional things here related to dementia group. We don't need to worry about that for right now. I am asking for predicted outcomes for these from this model because this data set includes the fake people as well. I'm also going to ask for what's called simple slopes. They're examples to try and illustrate what the interaction term is doing. So we ask for what the effective age would be at different levels of grip strength. We can also ask for what the effective grip strength would be at different ages. And to figure out how to write these statements, how to determine what the simple slope would be for any type of person, step 1, we go to the equation. If you don't like equations, go to the model line. Same difference. We need to pull out every single term that has the predictor in it for which we want the slope. So if I want the age slope, this thing that's highlighted right here, how many of these terms have age as part of them? 2, that's it. So to figure out how the model says the age slope would be, the only things we need is the age slope as a simple main effect and its interaction with grip. The rest is irrelevant. So based on my equation here, I'm pulling out the simple main effect of age. Remember what simple main effect synonym is? A conditional effect. It's the slope of that variable held specifically when all of its interacting predictors are 0. So I need that beta 1 and I need that beta 6. So I'm going to bring those down here. I'm going to factor out the age variable and stick it behind. So I'm left with this term in brackets, which is how the model tells me what the age slope should be. The age slope is just beta 1 whenever grip strength is 9, because that's when this term disappears. Otherwise, I have to know what grip strength is to be able to say what the age slope is. So these 3 sentences down here, these estimate statements, when you see the word, what it's actually referring to is the beta that goes with it. That's what SAS is talking about. So when I say I need 1 age 85, what I'm saying is I need one of the coefficients that goes with age 85, which is beta 1. So at a minimum, my age slope starts with the simple main effective age. I then fill in the value of the moderating predictor, which is grip strength here. So I fill in the value that should go with this part. If I want grip strength of 6, 9 minus 6, or 6 minus 9, excuse me, is minus 3. The second one is what it would be if grip strength is 9. Did I actually need to write this one, or is this going to show up somewhere else already on my output? Need to write it, or somewhere else?
Somewhere else.
Where is it going to show up? Because you're right. Where would this answer show up if I put this, say, in a homework, for example? It would be the beta 1. It would be in the solution for fixed effects next to the main effective age. That's what this means. So anytime you find yourself writing out one of these statements and only one thing takes a number, then you don't need the statement. It doesn't hurt to put it because then everything's in a nice, convenient, organized place. But this is what beta 1 means. The others, the first one and the third one, these are linear combinations. So the third one gives you the age slope when grip is 12, because 12 minus 9 is 3. Cole, are you frowning? Are you thinking?
No.
You're good?
No problem.
Okay,
I'm good.
great. Anyone else? Good? Good? Sorta? Maybe? I'll take maybe. Maybe's better than none. Likewise, go back up to my model here. If I want to know how to predict the effective grip strength for any kind of person, how many terms in that highlighted section do I need? Still just 2. I need the main effective grip and I need the age by grip interaction. Everything else is irrelevant. I think you're just squinting. I think that's what it is. I'm used to you sitting here and you don't squint as much when you're in the front row, so sorry. Don't mean to pick on you. I squint a lot. That's why. So same idea. We take the 2 things that we need. We factor out the variable for which the slope, factor out the variable that the slope is 4. I'll just say it that way. And then this part in brackets, that is how we get the grip strength slope. So beta 2 is the only thing we need to describe what the effective grip strength is when age is 85. Otherwise, we also have to know for what age do you want the grip strength slope. So I did the same thing, picking convenient values above and below the centering point. So this would be for an 80-year-old, because we've centered at 85. This one would be for a 90-year-old. So quick quiz. Did you know that back in the day, I never learned how to do this? I learned how to do this maybe 10 years ago, not when I was a student. Do you know how I was taught to do this? Like if you didn't know how to write these estimate statements, can you figure a way to trick it into getting this number right here that I have highlighted? No? So the reason that beta 2 is specifically the grip strength slope when age is 85 is because that is where age is centered. If I want beta 2 to become this one, I could recenter age. If I changed age to have a 0 point at 90, then the model directly gives me this one. And if I wanted to get the top one instead, recenter age at 80. Now, could you do this and get your homework correct? What do you think? Yeah. But do you want to run 3 models instead of 1? Exactly. It's a question of convenience. It's about recognizing that the one model gives you every permutation combination that you would ever think of. But yeah, that's what we did back in the day.
So if you center it to 80 or 90, where do you get the interactions?
The interaction would be the same because it's unconditional. But beta 2 would change as a function of where you centered age. So this grip strength slope is specific to age 0.
So I can get it from the estimate of the interaction.
Yes, you get it from the main effect.
Yeah.
The solution for fixed effects that shows up by default, you can manipulate your centering to get different variants. Yep. So I could get a different beta 2 if I manipulated where age was 0. Likewise, I could get a different beta 1 if I manipulated where grip was 0. Totally correct. It's a question of whether the thing you want is a linear combination of the model parameters or whether it is a model parameter itself. And then these, homework question, are the kinds of statements that you would have to write if you don't want to do fake people to create predicted outcomes in the presence of an interaction. So there are 2 things I want to make a point to note. When you are predicting y hat, intercept goes in. The entire model goes in for any value that is not 0. So in this case, because I left out sex and dementia, note from the first comment there, these are implicitly for sex is none and dementia, or sex is men and dementia is none. For the interaction term, where these numbers come from is literally the multiplication of the values that I filled in for their main effects. And so each of these statements will show up with a line that has an estimate, a standard error, a t-value, and a p-value. And margins is the same principle, except it takes less code. If you wanted to do this the long way in Stata, by the way, that would be lincom. You can write each of these as its own linear combination statement. So in Stata, for instance, this, let me find it, this line. That one line of code gives you these 9 lines in SAS. So you're asking for margins at, and then these parentheses, it goes from -5 in increments of 5 all the way up to 5. So it will give you every combination of -5, 0, and 5, every combination of -3 in increments of 3, so 0 to 3, and it's holding these other ones at 0. So one line gives you all of them. Okay, questions? Comments? All right, so then in our results, we looked at various things. So you know this part, right? You'll get a chance to practice it again. Name that letter. So our R square, 29% of the total variability in my cognition outcome is accounted for by the model. Do you see anything on here that tells me whether or not 29% is greater than 0? Which p-value? Our friend F. F is when you test more than one slope at the same time, such as when you're testing all 6 slopes that are part of our model. So, yep. How much variability in cognition is left over? Yep, that one. 86. Yep. These are the semi-partial eta squares. You can believe them for the ones that are not part of a categorical variable. I've got the next handout that goes into more of that, but I'm not asking you for any effect sizes on your homework because it's so squishy and different across programs. Okay, so here's my solution. So we have intercept. Definition of an intercept, go. Expected outcome or cognition when predictors are 0. So for this example, this is 29 is your cognition when you are age 85 with grip 9, and you are a male who does not have jaja. Woo! Now does this interaction term adjust anything that you just said? No. It will adjust what is predicted, but the definition of this intercept as what it is conditional on is the same, because you haven't added any new predictors. If you add a new predictor, then you have to further condition this intercept on where that predictor is 0. So, other homework question. These 3 slopes right here, conditional or unconditional? Unconditional. I'll ask the same question using different words. Marginal or simple? Which pair go together? It's tricky. Conditional goes with simple. Marginal goes with unconditional or main. So which set are these? Conditional simple or unconditional marginal? Unconditional marginal because they are not part of what? No interactions. Yep. That's why. In other words, this right here, this is a gender difference. Men are 0, women are 1. Who's doing worse? Women. So I would say that this is the shift from men to women, with men as the reference, meaning women pick up the coefficient, meaning women are -3. But that gender difference of -3 holds regardless of age, holds regardless of grip, holds regardless of dementia status. That's what I mean by unconditional or marginal. In contrast, this slope for age says for every year older you are, cognition goes down by 0.3, ... when what is true? When grip is 9. And the fact that you have to clarify that means you're in conditional or simple. It's not just the age slope for everybody. It is the age slope for grip is 9. Likewise, for every pound more you can squeeze, your cognition is predicted to be higher by 0.6, ... when age is 85, which means this is also conditional or simple. So now each of these constituent simple main effects can become more or less positive or negative as a function of this interaction. So let's do age first. And we did do this before, but it never hurts to review, especially since this is your last homework. For those of you who are just joining us, it's available. It's worth like 16 or 17 points, so like winner take all. But we're going over lots of stuff today to make sure that it's nice and straightforward for you. So the effect of age is negative or positive? Okay. Who can see the board? Or look at your handout in front of you. Either way. For those of you in the cheap seats, we'll make it bigger. Who am I kidding? These are all really expensive seats, am I right? You may not be paying in real dollars, but they're expensive. That's why I try so hard. I got to put on a good show for $17,000 a semester, right? Am I wrong? That is what graduate out-of-state tuition is around here. It's a $17,000 show. I may as well be Britney Spears in Vegas for that price. Okay, this number right here, positive or negative? Negative. So as age goes up, cognition goes down. Okay, so we've established this main effect is negative. That means the interaction can only do one of two things. It can make it more negative or less negative. Survey says? Less negative. Yes, the positive goes the other way. So minus 0.33 is the slope of age if grip is 9. For every unit additional grip, the age slope becomes less negative by 0.12. So the age slope is minus 0.3 when grip is 9. For every unit additional grip, that age slope becomes less negative by 0.12. In other words, is age bad for you? Is it bad to be old? Yeah. But when is it less bad to be old? If you're stronger. Because I'm stronger than yesterday. See, I can do Britney Spears, just not quite as well. Maybe not the right cohort for that joke? No?
No, I got it.
Got it? Stronger than yesterday. Okay, got it.
You're doing better than Britney.
I am singing live. I will give you that. I do not have a track or a backup dancers. Yeah. Well, I'm not dancing. You're going to have to pay for some extra tuition if you want to see that level of show. Or, bring me a few and then we'll talk. But so yeah, age is not so bad for you if you're strong. That's sort of the conceptual idea of what less negative. Give me some GRE words. Grip is what as a moderator? What is it doing to the age slope?
Protective factor.
Yes, protective factor. It's reducing the effect of age. It's mitigating. I like that one. That's one of my favorites. Weakening. Yeah? Any others? Deteriorating. Yeah, let's go with that. Although that's sort of like I picture like deteriorating by age, maybe. But yeah, but it does work. It does work. So yeah. Let's go the other way. This number right here, grip strength, positive or negative? Positive. So as grip goes up, cognition goes up. So that means the interaction term can do one of two things to it, right? More or less positive. Those are your only choices. What's it doing? More positive. So the grip strength slope is 0.6 if age equals 85. For every year older, that grip strength slope becomes more positive by 0.12. So is it good to be strong? Yeah. When is it more good to be strong? When you're old. Yeah. So age is doing what to the grip strength slope? More positive. Let's do some fancy words on that. Strengthening, I'll take that. Buffering, I do the other one. If it's less negative, to me, that's a buffering. Because that implies like a buffering is like bad. Sort of, it's bad. It's I like bolster. I like that one. Enhancing? Yeah, you get the idea, right? Because your reviewer is going to be like, more positive, what the F is that? And then you'll be like, no, it's enhancing. It's bolstering. They'll be like, oh, I get it now. And they'll really get it after you show them a picture. So we looked at a picture, I think. Did we? Maybe? You don't remember? Then we'll look at it again. Stronger than yesterday. Okay, now I have it in my head. Although it's better than the crap that my son keeps in my head. Children's songs are notorious for that. He's singing Christmas songs around the house now. My favorite is, I wish you were Merry Christmas. That's what his current one was. Last year it was, I wish it was Merry Christmas. He kept saying that, and I thought, that actually makes more sense. Because I wish it was Merry Christmas too, because, I'd be in my pajamas, hanging out. By the way, latecomers, we have oranges at the front of the room, if either of you want some. Yeah, no candy today, but oranges. So here's an example. Nature's candy, nice. Do you work at Trader Joe's by chance? That totally sounds like something they'd have on a billboard there. So we have age as the variable we care about in the picture. Different lines for different kinds of people, so that means grip is my moderator. That's the story. I've got the reverse plot next. So it's up to you which version you want to talk about. So the "you are here" sign of the plot is this square right here in the middle. That's grip 9, age 85. So everything is relative to that. So that means that this middle slope right here, that is the main effective age that is given directly by the model beta 1. The fact that this line is becoming more negative in people who are weaker and less negative in people who are stronger, that is the buffering or the weakening of the age effect due to grip. So the idea that the slope is less negative is conveyed by these different slopes. If you wanted to go the other way and talk about the effective grip, the effective grip that's given by the model is implied by the vertical distance between these things, but it's not exact because these are, 3 points apart as opposed to 1 unit. But this is the point where the model's talking about. These get more spread out as you get older. So grip matters more in old people. It matters less in younger people. So at some point along this x-axis, this vertical difference is significant and it becomes non-significant. You see over here, they're on top of each other. At some point, this spread becomes significant. Likewise, these lines, this line happens to be significant. This one is, we don't know at what point it becomes non-significant. And so this is where our simple slopes can help us because we actually know the answer to whether or not these particular differences in slopes are significant. We ask for that information. So right here, these are the results of our estimate statements. These are our simple slopes. Okay, so here's my 3 age slopes that we asked for. The middle one is the one that's given by the model, so it's kind of here as a reference. So the effective age is negative at grip equals 9. It becomes less negative as grip increases. By the time you get to age 12, the slope is actually non-significant. So somewhere between grip 9 and grip 12, age stops mattering. Age does matter if you're grip 9 or lower. But if you go this way, it's negative, negative, negative forever. So it's pretty much like if you're super weak, age is always going to matter. At some point, it stops mattering, somewhere between 9 and 12. What's eventually going to happen if I keep going? What direction is this headed? It's heading positive. So eventually, if I keep going high enough in grip, this age slope is going to be positive. So the idea that we want to find the points at which this slope turns on and turns off, so to speak, that's the idea of regions of significance. So we're taking the T formula to describe the slope significance, flipping it around to find the slope value that renders a significant T in the negative direction and in the positive direction. That's what the formula is trying to do. I'm not asking you to do this in your homework, by the way, so don't panic. But I do have a SAS macro that I wrote that does it, and I have an Excel spreadsheet that does it as well. And so here is the same idea, putting grip strength as the x-axis and age as the moderator, where the square in the middle again is the "you are here" sign. That means this middle line is the slope of grip beta 2 that's directly given by the model. And the grip strength slope becomes more positive in people who are older. It becomes less positive in people who are younger. And we can go up to these three values here and see what happens. So grip matters if age is 85. It continues to matter more as age increases. And somewhere between age 80 and age 85, grip stops mattering. So we can look at the region of significance that way as well. So if you are interested in doing this regions of significance thing, I can give you two resources to do it. This is example 7. I did an Excel spreadsheet. I can show you the input that you need to have, because I wasn't able to make a macro for Stata. I'm not that skilled in Stata to be able to do that. Let's see, here we go. So equation 2.9, for instance, this is from the book, actually. I made this for the book's website. You would have to enter the slope for the predictor, the standard error for the predictor squared, the interaction effect, the slope or the standard error of the interaction squared, and the covariance of the interaction and the predictor, standard error. Now that is the one that you have to request a special piece of output that's kind of tricky to find. So I've found two ways for you to be able to do this. In SAS, there is another procedure that we haven't seen yet, but which is my bread and butter in teaching mixed models. As you might guess, it's called Proc Mixed. So this is how you do general linear type models when you have more than one type of sampling. So if you have occasions sampled longitudinally over time for multiple people, if you have multiple students within multiple classrooms or schools, that kind of thing, general linear models that allow you to predict that kind of stuff at the same time. Well, a special case of that is when you only have one level of sampling. And if you run the same model that we just finished using mixed instead of GLM, one of the options that you can ask for on the model statement is this thing called COV-B. That is where you get the covariance between the standard errors for the interaction term and the predictor of interest. That extra piece of output is what you need, which is right here. And I know this sounds sort of crazy to think about, but this is roughly how the estimates for your slopes are related to each other, is the way that you can think about it. On the diagonal is the standard error for each of your slopes or intercepts squared. And so the values that you need to be able to do regions of significance, you need the standard error squared for the predictors of interest, for the interaction term, and you also need the covariance between each predictor and the interaction term. I don't think I highlighted those, but they should be in here. So if you use the macro that I wrote in SAS, it asks you to save different pieces of data sets to be able to use this, and it spits out these numbers. Otherwise, you can put the numbers in here, and it spits out the numbers in the bottom. So the results then, if we do the effect of grip as the thing we care about and age as the moderator, then here are the limits, 70 and 82. So let's go back up to the slopes here. So for these slopes, if I have grip strength slope here, so we're talking about when do these slopes become significant? That's what we're talking about. So long as I have age that is greater than or equal to 82, so that'd be a line kind of like in here between these two, that line and anything for an older person is significantly negative. That's the demarcation. Anywhere between 82 going up to 70 would be non-significant, and anything past 70 would be significantly positive instead, or negative instead, excuse me. Gotta do my elbow. So why would you care? Well, you'd want to look back to your sample and see what the distribution of age looks like, and to see sort of for what percentage of your sample you would actually expect a negative effective grip, a positive effective grip, or no effective grip. And in this sample, it's most of the people are 82 or above, So for most of these people, the effective grip would be positive. For relatively few, there would be no effective grip. And since there's nobody who's younger than 70, there's no case in which more grip strength is bad for you. Likewise, if we do the effective age, those numbers worked out to be 9 and 18. So age is bad for you. Anytime you hit 9 pounds or lower, so these are significantly negative. From 9 pounds up to 18 pounds, it's non-significant, and anything over 18 pounds would be significantly positive. In our sample, about half of the people had 9 pounds or fewer, so half the people would have a negative effective age, half the people had 9 pounds or more, and so they would have a non-significant effective age. Nobody had more than 18, so they would not have a positive effect. So this allows you a little bit more description in terms of exactly when your effects of your predictors matter or not. So I like it as a useful supplement to these sorts of simple slopes kinds of things. How are we doing? Doing eh? Here's another one. Let me pull up lecture 7. I did another example of that. Regions of significance. If I had a simpler model that had only age and gender in it, so this is slide 19 of lecture 7. So in this case, we're talking about the gender difference at different ages. So beta 2, the main effective gender, the simple main effect, is minus 0.53 at age 85. Beta 3 is how that gender difference varies as a function of age. So if you look at the direction of these two coefficients right here, what is happening to my gender difference as age increases? Which pattern is this? So beta 2 is my gender difference. So women do worse by half a point if age is 85. The interaction term between age and gender is minus 0.1. So what is that interaction term doing to my negative effective gender? It's making it 2 negatives. It's more. It's more. So as age increases, this gender difference becomes more negative by 0.11 per unit age, per year of age in this case. So we know that it's significant at age 85. We might want to know at what point does it become non-significant as age decreases. And I worked out the numbers, and it works out to be 60 and 80 or so as the cutoffs. So that means that anytime above age 80, there is a negative gender effect such that women do worse. Between 60 and 80, the gender effect is non-significant. Anywhere below 60, the gender effect reverses such that women do better. So you'd have to ask yourself, is there anybody below 60 in the sample? Like, how does the sample distribution of age compare to these regions? So for whom is the gender difference positive, neutral, or negative? That would be the question. Now, do I need to do this sort of thing to go the other way? What if I were interested in describing the age slope and gender is my moderator? Do I need regions of significance? Let me say it again, another way, in a way that makes it more obvious what I'm saying. Do I need regions of significance? No. In this simplistic example, gender is binary. So I could figure out what the age slope is for a man, what the age slope is for a woman, the end. And beta 3 tells me whether those two slopes are different. Now, what if I decided to make this not simplistic? What if I allowed for other options, like non-binary, for instance? I could do the same exact thing, albeit with another level of complexity. Then I would have 3 possible age slopes. I would have the age slope for men who identify as men, identify as women, and identify as neither, right? Or non-binary, however you want to phrase it. There's at least 3 then. However, could I have just one beta 3 to tell me whether or not those 3 slopes are different numbers? No. How many different interaction terms do you think I need to differentiate these 3 fingers? 3 or 2? I only need 2 because the third is going to be a linear combination. So the exact same principles that you learned for main effects of categorical predictors apply to interaction terms. In that case, if I wanted to add a third category for gender, I would have to add another simple main effect of gender, differentiating one of the other categories, as well as another interaction term of age with that other main effect. So that is where we are headed next, friends, is interaction. She's like, are we really headed there today? I was wondering the same thing. But that's where we're headed next, is trying to figure out how to do interaction terms among categorical variables. It's very straightforward if your predictor is either quantitative or binary, in that it's represented by one slope. It's less straightforward because it requires more than one interaction term if either predictor is characterized by more than one slope. So for example, if I have gender as 3 categories, that means I need 2 main effects to differentiate my 3 categories, and I need 2 interaction terms with age to differentiate the 3 possible age slopes. Likewise, if I just have age like this, what kind of pattern of effect am I saying age has? Negative, looking for a word that starts with L. Linear. Do you think it's a reasonable thing to think that age has a linear effect, or is there a point at which age sort of doesn't matter as much? Or matters more, right? If you think of it like a decelerating curve. How would I operationalize this idea that age doesn't matter as much as you get older, or it matters even more as you get older? Exponential curve would be one. Another kind of interaction term that makes something non-linear that was linear starts with a Q. Quadratic, yeah. Or what if I have a hypothesis that says after 65 everything goes to shit? I have a before and after, like retirement is bad for you, something like that. How would I operationalize that sort of idea? Piecewise, right? It'd be like, before 65, you're fine, and go to shit like after that, right? Piecewise. So in any of those cases, however you want to think about it, age would be characterized by more than one slope to induce the curvature or to induce sort of the break point. And then in that case, we would have to have an interaction term of gender with each piece. Maybe women don't go to shit as fast as men. How about that? Right? That would be a gender by second slope kind of thing. So anytime you have a predictor variable that is characterized by more than one slope when it's a main effect, and interaction with it, same deal. Or maybe men go to shit less quickly. I don't know. I'm not trying to like be sexist or anything. I'm just trying to be funny. You're paying $17,000 a semester for this. It better be good. If I can't be Brittany, then maybe I can be, like the puppet guy or something, right? Or, I don't know, who's your favorite comedian? No. I'm a big fan of Dennis Leary still, but most of his material is not appropriate for the classroom. Ellen DeGeneres, also funny, yes. I saw Paula Poundstone once and funny. She was very funny. So, no? I used to like Louis C.K. Yeah. So many people. So many people. All right. I'm off on a tangent here.
I got my husband to get to Sebastian Maniscalco.
I don't think I know
He's an
him.
Italian. He's really funny. He's from Chicago.
Oh, I know who my favorite comedian is. It's Fluffy. Gabriel Iglesias. Yeah, he goes by the nickname Fluffy. He says, "I'm not fat, I'm fluffy." It's like his thing. It's he's very funny. But George Lopez, also funny. Yeah, so there's a lot of funny comedians.
Yeah.
And I bet you didn't have to pay $17,000 for a ticket to see them. So if you did, it must have been really good seats. Let's put it that way. So yeah, that's what I'm trying to set the stage for here, is the idea that if each predictor itself has to be characterized by multiple slopes, then so do its interaction terms. All right. You think that's enough for today? Yeah. For the whole semester? No, we got one more week, man. I know.
It's just gone so well. So
Just leave it. No, everyone's doing fine. It has gone well. Yeah. You sound surprised. You should. No, I'm trying to set you up for other things that would be helpful to you that I won't necessarily give you tests on or whatever, but that would be useful. So things like ANOVA with a hole in it.
Oh my God.
No, that happens. It's when you have a design where you're supposed to have like 3 categories of one variable and 2 categories of another, and so there's supposed to be 6 combinations, and someone messes up and one of them's not there. What do? I'll teach you. Come back next week. I'll tell you. All right. Yeah, let's just call it a day, folks. Office hours are this afternoon if anybody wants to get a jump start on your homework. Otherwise, I will let you know when your quiz is available. Please work on it before next Tuesday so we can go over it. It will be practice with interactions.
Monday night though, right?
Yeah,
Okay.
I've been sort of loosey-goosey with that. The idea being come ready to class to be able to talk about it. And again, you get a point just for doing it, or 2 points. So, okay? Okay, have some oranges as you go if you want, and otherwise I'll see you next week.